Hey there, Year 12s. With this problem here, the TSSM Exam 1, um, this here is a composite function skill, exercise 1E from the Methods Cambridge textbook. Uh, when you're dealing with this, you don't need to specifically know what the graph looks like. So I don't personally know what it looks like, but I can kind of predict it. And you need to be able to break it up into its two functions because this is a composite function. And what I'm seeing here is something like there's a quadratic function. So I could say something like let g of x equal to x squared plus x minus 30, right? So it's a quadratic graph. I mean, just looking at that type of equation, I can already predict that it's going to be a positive shape. It's got a y-intercept at negative 30, 0, negative 30. So when x equals 0, and x-intercepts, I'll probably see if I can factorize it. So what's this? Maybe 6, 5. Yeah, that works out. Okay, so then you've got x-intercept at 5 and x-intercept at negative 6. So say negative 6 is over here and 5 is over here. So it probably looks something like that for the parabola. Okay, so this is key. This is the y values. These are the x values for the parabola g of x. Okay. And then what it's also now saying is that you're going to then take those values, whatever those y values are, you're going to then square root them. So if you think about the composite function the way I taught it for 1e, you see essentially it's f of x. If I said h of x was equal to root of x, and yeah, I think that that should be all right. No, negative root of x, because I think it was, there's this negative at the front. And then I said g of x is equal to the quadratic, right? And then I said f of x is equal to h of g of x. Can you see that? So I split it up into two functions. Then what this is saying is sub g of x into h of x. And that's how you end up with negative of square root of x squared plus x minus 30. Okay? Now in this composite function, what this implies is that when you sub x into the function, this composite function, it has to go through g of x first. So the way I explained it in class with 1e is that you got to think of it as, all right, what you put in is the domain. So this is the domain of g. Domain of g goes in, and it goes through the conditions for g of x, which is a parabola, right? And then it spits out a y value, which is the range. So this is the range of g. So ran of g, right? But when it spits out the range of g, it then has to go into a new function, another one, and this one now is the h of x function, which remember it was the negative root of x. And this is one of the reasons why when you first do composite functions, you have to generally picture what the domain and range would be. So say the domain, the range, and g of x, and then h of x, right? We can see that you can sub any number in for a quadratic. Doesn't matter what x values you sub in, there will always be a y value, right? A corresponding y value, because that's your y-axis. So it seems like there is no restriction for the domain of g, and the range can be, actually it's not all real values because there's a turning point somewhere here, and it goes on to infinity, right? We can quickly find the turning point. It's the middle of negative 6 and 5. So 6 plus 5 divided by 2. What's that? Negative, so negative half. Oh, I can't be bothered. But yeah, you would sub it in here, and then you get your y value. Okay, so the point is, I'm trying to say that I must well calculate it actually. I was hoping that the numbers would work out nicely. But okay, g of negative half, because technically I don't need to know this bit, but I'm going to do it comprehensively just so that you can visualize the graph. Because the better you can visualize g of x, what happens to the first function, then the better you can visualize what will happen in the second function. That's so hence graphing each one and analyzing it is going to be key. But anyways, g of negative half, so I'm going to sub in negative half squared. Actually, it might be easier if I subbed into the factorized one. So negative half plus 5, or minus 5, sorry. Minus 5, and then negative half plus 6. That gives you negative 5.5. And that's what? 5.5. Okay, so we're getting roughly... Oh man, that's what? Negative 5.5 is the same thing as 11 on 2 times this is 11 on 2. So let's change that to negative 121 on 4. Okay, cool. So the range is at negative 121 on 4 all the way to infinity. Okay, so just for argument's sake, we can see the range is from negative 121 on 4 all the way to positive infinity. So that's for g of x. Now, this is where the key part is. So the y values that spit out, so remember, you can put any number for x element of real numbers. You can put any number into g of x, but then g of x has to spit out any of these numbers here. So it's between negative 121 on 4 to infinity. Okay? And here's the thing that we really try to calculate. Whatever those numbers are, can they all fit into h of x? See, but then h of x has an implied restriction. So now if you visualize what h of x looks like, if I told you, let's picture what h of x looks like now. H of x is root of x, and we know root of x normally looks like this. But with a negative, that's a reflection on the x-axis, so it'll look like this. And so this is our graph. But if I asked you, what is the domain and range of h of x? Well, you would say that, well, the domain can only be 0 to infinity, so 0 to infinity. And that means here, domain is 0 to infinity are the only numbers that h of x can take. Because whatever you put in, that is the x values, right? But those x values are actually the range of g. That's why the condition in exercise 1e was that range of g needs to be a subset for the domain of f, or in this case, h. Okay, it needs to fit. Otherwise, there'll be a problem here. So the problem is that I can't take any number. I can only take from 0 to infinity. But if you look at the range, the list of numbers that you could potentially put into h of x, there's a problem. Negative 121 on 4 is already a problem. That's a negative number, and we already know you cannot square root a negative number. And this is where you can then kind of picture what's happening, and that's where you can kind of fix what's happening. So let's go back to this graph here. So I'm going to try to rub everything out so you don't get confused. I might as well draw it all again. I'm going to draw it again. Here we go. So we have figured out it was negative 6, 5. Turning point was like negative half to negative 121 on 4, I think it was. And then the y-intercept was 0 and negative 30. Okay, cool. Now, here's the thing that you have to, this is the main thing of exercise 1e to take away. You see, what couldn't we use from this g of x? When did it become a problem? So the problem came about this bit. Negative 121, that range, anything that's a negative that you're going to decide to put into h of x is a problem. So if you visualize this graph, negative 121 on 4 is here. And essentially any negative y value, so any part of the graph of g of x that is below the x-axis, which really, this is the graph. This is the graph, the section where you can't sub any numbers in into h of x because it will be negative. So if you're confused what I'm saying here, what I'm saying is even if you sub 0 in, if you put in, so let's think about the machine again. If you put in x equals 0, we already knew that the y-intercept was y value is negative 30. But you can't sub negative 30 into h of x because then h of negative 30 becomes negative root of negative 30. That's undefined. So can you see, I don't need to guess these numbers. I can actually look at the graph and realize that actually what domain, what x values can't I choose? Any numbers that in between, negative 6 and 5. Any number that you choose anywhere between will correspond to a negative y value. Can you see that? every x coordinate here corresponds to a negative y value. So what this tells me then, if g of x, remember I'm going to draw the machine again, g of x, you can put in any number you want. The problem occurs right here. The y value, the range for g, I'll call it random g. The problem was that it would include negative 121 on 4 to infinity. I can't have negative 121 on 4 to at least up until 0 because the y values, I need the y values to be positive or 0 at minimum. So the only ones I can accept is from 0 to infinity because remember the domain of your h of x, okay, the domain of h of x, you can only square root 0 and bigger. So this is where you look at the graph and say, well, okay, I need to fix my x values so that my range is fixed, so that it can only get 0 to infinity. So if you look at the graph again, I'm just going to rub these highlighted bits out. I'll just do it all again. If you look at the graph again, this is 5, this is negative 6. The only parts that is not, range is not negative, is this bit, this part of the graph and this part of the graph. These are the only two parts of the graph where the y values are positive. Can you see that? Like this point here corresponds to an x value, but then the y value is positive. Only these sections correspond to a positive y value. So when you say, what does the graph look like? Well, let's interpret it logically, okay? We can already see that the x values cannot be any real values. You have to choose it from greater than 5 and less than negative 6. So that's the first thing you needed to be able to see, that x had to be an element of negative infinity up until negative 6 inclusive, union from 5 to positive infinity, right? Now, that's just for the first bit. It says find the implied domain. So I would have answered that question, and that was the biggest part. Okay, so the biggest part, A, I now know the domain. That will guarantee that the range of G will be from 0 to infinity. Okay, so if you choose any numbers greater than 5 or less than negative 6, you'll guarantee that the y values will be positive. Then afterwards, okay, in part B, how do you know the range of the function, right? Given that you don't even know what the graph looks like. Well, you can kind of predict it because if you know that the quadratic graph, so just the quadratic graph, g of x, right? We know that it looks like this bit based on the new domain. So the new domain was from negative 6 and below, and the other one is from 5 and above, right? So the y values, these are the ones you're subbing in. But when you sub it in, what y values are you substituting? It's 0 to infinity. And these are all the coordinates that you currently have for g of x, okay? Then what happens when you sub all of those coordinates, the y values, into h of x? So when you sub it into h of x goes, I'm going to square root that g of x, and then I put a negative in front of it, right? But when you square root, just take it step by step. When you square root all of those values, every one of these coordinates, all those y values, are going to be square rooted. Now, what happens when you square root a value? Think about it like square root of 25, does it get smaller or bigger? Square root of 16, does it get smaller or bigger? Square root of 4, does it get smaller or bigger? Hopefully you figured out there's a trend, it gets smaller. But even though it gets smaller, it's still going to be somewhat a parabolic shape. True? It's just smaller. It's just flatter. That's a better way of picturing it. So at the end of the day, the root of g of x would still look something like this, from negative 6 to 5. And then at the end of the day, remember, there's a negative at the front of it, so all it does is a reflection, and it just looks like that. So even though I don't fully know what the graph might look like, I can already say that the range of the function, after going through g of x and then going through h of x, the result must be 0 and all the way to negative infinity or negative infinity to 0. So I know the range must be from negative infinity to 0, just simply because of that reflection. Does that make sense? Okay, and then is this a one-to-one function? Well, clearly, just even looking at this, we can tell it's not. A horizontal line test will prove that that wouldn't be true. But again, even if you didn't know that, the logic to it is that in a quadratic graph that we had, if this was 5 and this was negative 6, even if you picked like 1 unit across, which makes it 6, and then 1 unit to the left, which is negative 7, they will share the same y value. Get me? Because it's symmetrical, right? It's symmetrical because in a quadratic graph, the turning point cuts it in half. So if at negative 6 it's 0, and then at 5 it's also 0, then if you went 1 unit across, so to 6, and then 1 unit to the left, it's negative 7, they must share the same y value. And that's a problem already, because if you have the same y value, okay, which means, remember, let's think about the machine again. G of x, if I sub in x equals to 6 or x equals to negative 7, it will spit out a y value that is exactly the same, whatever that number is. And that range value goes into h of x, right? And then that will have to spit out the exact same h of... so what I'm trying to say is, at the end of the day, that hybrid function, or the composite function, f of, if you subbed in 6, should be equal to f of negative 7, logically. Yeah. So these two values, which corresponds to this one, that y value will be the same. So when you sub it in, even though it started off with a 6 there, you'll actually end up with the same value. So that's a problem, because that means you had many x's. See, many, it's different x's, and you end up with exactly the same y value. So it's many to one. It's a many to one function. So clearly it's not a one-to-one based on what we can see so far. Okay, so it's and this is where, at the end of the day, did I know what the graph looks like? I kind of do, but you didn't also need to as well, and you didn't need a CAS for that as well. But it's about the analysis of the quadratic and how that influences the conditions of a square root. And that's a very typical exercise 1E skill that students need to be able to take in. So I know it was a bit of a long explanation, but I'm hoping to get that point across, that you have to analyze in two parts. And it could be in any function. It could have been a square root with a 1 on x function in there. It could have been a 1 on x function with a quadratic in there. And you have to know the properties of each function and then picture what would happen and what are some restrictions. That's probably one of the biggest challenges, I would say, that students will find to get their head around 1E. And that's why this is a good practice, because it is pretty much the bare minimum when it comes to Chapter 1 exam-style question. That's usually what they would chuck in and expect students to know. So, yeah. I hope that explanation gives you a bit of a direction there, but definitely have a look at exercise 1E, look at the chapter review, see if you can find more composite functions more similar, or you can make up some yourself and then see if you can picture it and then type it on Desmos or your graphics calculator to see if you had the range and domain correct. That's a good way to practice your analysis skill. And stick to the basic graphs that you learnt in year 11. So, for example, you should have the quadratic graph, you could have a root x graph, you could have a 1 on x graph, you can have a 1 on x squared graph, you can have a linear graph. Those are good combinations that you can mix and play around with. Those are like standard. And then when you want to make it more complicated, that's when you chuck in like logs but we're not doing logs for the SAC, so in this case, you probably play around with mainly these ones. That should be good enough. Yeah, and chuck in cubics too if you wanted to. But yes, hopefully that clarifies how to solve that problem.